Welcome to this problem walkthrough. In this session, we will explore LeetCode problem number 1413, titled Minimum Value to Get Positive Step-by-Step Sum. This problem challenges us to determine the smallest positive start value that ensures a cumulative step-by-step sum remains positive when iterating through an array. Let's dive in and break it down step by step. In this problem, we are given an integer array called nums, and the goal is to determine the minimum positive value of start value such that a step-by-step sum remains at least 1 throughout the process. We begin with an initial value, start value, and at each step, we add the current element of the array to the running sum. If at any point this running total drops below 1, it means start value was too small, and we need to increase it. Our task is to find the smallest possible value for start value that ensures the sum stays at least 1 for the entire array. The input is a list of integers representing the array, and the output is a single integer representing this minimum value of start value. To understand the problem better, let's look at an example. Here, the input array is nums equals -3, 2, -3, 4, 2, and the output is 5. Starting with start value equals 5, we calculate the step-by-step sum. Initially, the sum is 5. Adding the first element, -3, gives us 2. Adding the next element, 2, results in 4, then subtracting 3 gives 1. Adding 4 increases the sum to 5, and finally, adding 2 results in 7. Notice that at no point does the running sum drop below 1. Therefore, start value equals 5 is the minimum value that satisfies the condition. Here's another example. The input array is nums equals 1, 2, and the output is 1. If we start with start value equals 1, the initial sum is 1. Adding the first element, 1, brings the sum to 2. Adding the next element, 2, results in 4. Throughout this process, the running sum stays above 1, so the minimum start value is simply 1. This example demonstrates that when all elements in the array are positive, the smallest possible start value is always 1. In this example, the input array is nums equals 1, -2, -3, and the output is 5. Let's see why. Starting with start value equals 5, the initial sum is 5. Adding the first element, 1, increases the sum to 6. Adding the next element, -2, brings it down to 4, and then subtracting 3 further reduces it to 1. Even though the sum decreases, it never drops below 1. Therefore, the smallest start value that ensures the step-by-step sum remains at least 1 is 5. Now, let's consider the constraints and edge cases. The array can have between 1 and 100 elements, with each element ranging from -100 to 100. For edge cases, if the array contains only positive integers, such as nums equals 2, 3, 4, the output will always be 1 since the sum will never go below 1. On the other hand, if the array includes large negative numbers, like nums equals -100, -50, 200, we need to account for the lowest point the cumulative sum reaches before recovering. For single-element arrays, such as nums equals -5 or nums equals 10, the solution tests whether the single value can keep the sum above 1 or requires adjustment. These examples and constraints help highlight the range of scenarios this problem addresses. To solve problem number 1413, the goal is to find the smallest positive start value such that the cumulative sum of the array nums never drops below 1 at any step. One straightforward way to approach this is through a brute force method, where we start with start value equals 1 and simulate the step-by-step sum. If at any point the cumulative sum falls below 1, we increment start value and repeat the process. While this method is simple to understand, its implementation involves repeatedly looping through the array for each tested start value, leading to a time complexity of O and *k, where k is the number of increments required to find the solution. This makes it highly inefficient, especially for larger arrays or extreme values. Instead, we can consider an optimized approach that avoids this repetitive testing. By calculating the cumulative sum just once and tracking the smallest value it reaches, we can derive the necessary start value mathematically. If the minimum cumulative sum is min sum, then we know that start value must be at least 1 min sum to ensure the sum remains positive throughout. This insight eliminates the need for trial and error, offering a far more efficient solution. The optimized approach can be implemented in 2 simple steps. First, we calculate the prefix sum of the array nums while keeping track of the minimum cumulative sum encountered during the process. Next, we use the formula start value equals max 1 min sum to determine the smallest positive value that guarantees the sum remains positive at every step. This method has a time complexity of O(n), since we only need to iterate through the array once, and it requires constant space, O(1), as no additional data structures are used. The advantages of this approach are clear: it's efficient, scalable, and handles edge cases seamlessly. By focusing on the minimum cumulative sum, we avoid redundant computations and directly compute the result. This makes the optimized approach not only faster but also simpler to implement compared to the brute force method. For these reasons, it stands out as the preferred strategy for solving this problem. When comparing the two approaches, the trade-offs become evident. The brute force method is easier to conceptualize but suffers from poor scalability due to its high computational cost. It becomes impractical for large arrays or extreme input values. On the other hand, the optimized method is both time and space efficient, making it the clear choice for this problem. By leveraging the prefix sum and tracking the minimum cumulative sum, we reduce the solution to a single pass through the array and a straightforward mathematical calculation. In conclusion, the optimized approach stands out for its efficiency, clarity, and scalability. It ensures correctness while minimizing computational overhead, providing an elegant and practical solution to the problem. To solve this problem, we need to ensure that the cumulative sum of the given array never falls below 1. The challenge is to determine the smallest positive value for start value that satisfies this condition. First, let's understand the problem mathematically. The cumulative sum at any index I is calculated as sum I equals sum I1 plus nums I. To ensure the cumulative sum is always at least 1, we need sum I equals 1 for all indices. This means that if we start with the correct start value, the cumulative sum will never drop below 1 throughout the array. To achieve this, we'll simulate the cumulative sum step by step while keeping track of how far below 1 the sum might drop. This will help us calculate the minimum start value needed to keep the sum positive. Now, let's break the solution into concrete steps. First, we initialize two variables, cumulative sum to 0, which will keep track of the running total as we iterate through the array, and minimum sum, which will record the lowest value of the cumulative sum encountered. Next, as we loop through the array, we update the cumulative sum by adding each element, nums I. After updating, we compare the current cumulative sum with minimum sum and update minimum sum to always hold the smallest value seen so far. When the loop is complete, we use the value of minimum sum to calculate the required start value. If minimum sum is already greater than or equal to 1, then start value equals 1 is sufficient. However, if minimum sum is less than 1, we calculate start value as 1 minimum sum. This ensures that the lowest cumulative sum, when adjusted by start value, will be exactly 1. Finally, we return this start value as the result. This approach is based on a couple of key insights. First, tracking the cumulative sum allows us to identify the exact point where the sum might fall below 1. By keeping track of the smallest cumulative sum encountered, we can calculate how much of a buffer is needed to bring the sum to at least 1. Second, this method is highly efficient. Instead of trying multiple start value values, which would be computationally expensive, we directly compute the solution by deriving it from the minimum sum. This reduces the time complexity to O(n). Additionally, the algorithm handles edge cases gracefully. For example, if the array contains only positive numbers, the cumulative sum will always remain positive, and the start value will simply be 1. On the other hand, for arrays with large negative values, the algorithm ensures that the calculated start value compensates for any deficit, no matter how large. In terms of implementation, the solution is both simple and space efficient. We only need two variables, cumulative sum to track the running total of the array elements and minimum sum to record the smallest cumulative sum encountered during the iteration. No additional data structures, such as arrays or lists, are needed. This makes the solution highly space efficient, with a space complexity of O(1). For the time complexity, since we traverse the array exactly once and perform only constant time operations at each step, the overall time complexity is O(n). This efficiency makes the algorithm suitable for handling large inputs. Let's walk through an example to see the algorithm in action. Suppose the input array is nums equals -3, 2, -3, 4, 2. We start by initializing cumulative sum equals 0 and minimum sum equals 0. Iterating through the array, we first add nums 0 equals -3 to cumulative sum, giving cumulative sum equals -3. We update minimum sum to -3. Next, adding nums 1 equals 2 results in cumulative sum equals -1, but minimum sum remains -3. Adding nums 2 equals -3 brings cumulative sum equals -4, so minimum sum is updated to -4. For nums 3 equals 4, cumulative sum becomes 0, and minimum sum stays -4. Finally, adding nums 4 equals 2 gives cumulative sum equals 2, with minimum sum still at -4. After the loop, we calculate start value equals 1, minimum sum equals 1, -4 equals 5. This ensures that when we add 5 to the cumulative sum at each step, the sum will always remain positive. The output is 5. This implementation solves the problem by iterating through the input nums array and calculating the cumulative sum step by step. The goal is to ensure that the cumulative sum never drops below 1, as specified in the problem. The variable current_sum keeps track of the cumulative sum as we iterate through the array. Simultaneously, min_sum is updated to store the lowest cumulative sum encountered during the iteration. If min_sum is negative, it indicates the cumulative sum has fallen below 1 at some point. To ensure the cumulative sum remains positive, the minimum start value required will be 1 min_sum. If min_sum is non-negative, the cumulative sum is always at least 1, and the start value can safely be 1. This approach is efficient with O(n) time complexity, where n is the length of the input array, since it involves a single pass through the array. The space complexity is O(1), as no additional data structures are used. This is the Java implementation of LeetCode problem number 1413, minimum value to get positive step-by-step sum. The logic mirrors the provided Python solution, maintaining the same approach of iterating through the array, calculating a running sum, and tracking the minimum sum encountered. Key differences include Java-specific syntax, such as type declarations, int for variables, and using math.min for comparisons. The function returns the minimum start value required to ensure all step-by-step sums are positive. Let's begin with the first example where the array is nums equals -3, 2, -3, 4, 2. To solve this, we start by initializing two variables, min_sum and current_sum, both set to 0. Now, we process each element step by step. First, for the element -3, we add it to current_sum, resulting in a value of -3. At the same time, we update min_sum to be the minimum of its current value, 0, and current_sum, which gives us -3. Next, we move to the second element, 2. Adding it to current_sum gives -1, and we again update min_sum to the minimum of -3 and -1, keeping it at -3. Then, for the third element, -3, adding this to current_sum results in -4, and updating min_sum now gives us -4. This process ensures we are tracking the lowest cumulative sum encountered so far. Continuing with the same example, we now process the fourth element, 4. Adding 4 to current_sum brings it back to 0. When we update min_sum, the minimum of -4 and 0 remains -4. For the fifth and final element, 2, adding this to current_sum gives a value of 2, and min_sum stays at -4, as it is the smaller value. After processing all elements, we calculate the result. Since min_sum is less than 0, we determine the minimum starting value needed to ensure all step-by-step sums are positive by computing 1 minus min_sum, which is 1 minus 4, resulting in 5. Therefore, the output for this example is 5. Now, let's look at the second example where nums equals 1, 2. Again, we initialize min_sum and current_sum to 0. For the first element, 1, adding it to current_sum gives 1, and updating min_sum results in the minimum of 0 and 1, which is 0. Next, for the second element, 2, adding this to current_sum produces a value of 3, and min_sum remains unchanged at 0, as it is the smaller value. After processing all elements, we check min_sum. Here, since min_sum is greater than or equal to 0, the minimum starting value required is simply 1. Therefore, the output for this example is 1. For the third example, nums equals -1, -2, -3, we start with the same initialization, min_sum and current_sum are set to 0. Processing the first element, -1, we add it to current_sum, resulting in -1, and update min_sum to the minimum of 0 and -1, giving -1. Then, for the second element, -2, adding it to current_sum produces -3. Updating min_sum now yields -3 as it is smaller than -1. Finally, for the third element, -3, adding this to current_sum gives -6, and min_sum is updated to -6. This step-by-step tracking helps identify the minimum cumulative sum throughout the process. To complete this example, we perform the final calculation. Since min_sum is less than 0, we find the minimum starting value needed by computing 1 minus min_sum. Here, 1 minus 6 equals 7. This ensures that all step-by-step sums remain positive when starting with this value. Therefore, the output for this example is 7. The time complexity of the solution is O(n), where n represents the length of the input list, nums. This is because the algorithm processes each element of the list exactly once. It uses a single for loop, and during each iteration, it performs two main operations. First, it updates the cumulative sum, current_sum, by adding the current element, which is a constant time operation. Second, it updates min_sum by taking the minimum of the current min_sum and the updated current_sum, which is also constant time. Since these operations are O(1) and the loop runs n times, the total time complexity becomes O(n). Importantly, this holds true for all cases best, average, and worst, because the number of iterations is always determined by the size of the input list, not the values within it. The space complexity of the algorithm is O(1), or constant space. This is because the solution only uses two variables, current_sum and min_sum. These variables store the cumulative sum and the minimum cumulative sum encountered so far, respectively. Regardless of the size of the input list, the memory usage remains constant since no additional data structures, like arrays or hash maps, are required. Furthermore, the input list nums is not modified during the computation. This makes the algorithm highly space efficient, as its memory usage does not depend on the size of the input. To understand the efficiency of the current solution, we can compare it to a brute force approach. In the brute force method, we would test all possible values of start value starting from 1, and for each value, calculate the step-by-step cumulative sum to check if the condition of a positive sum is satisfied. This would involve nested loops, an outer loop to incrementally test each start value, and an inner loop to calculate the cumulative sum for that start value. The time complexity of this approach would be O(n*(m), where n is the length of the input list nums and m is the number of candidate start value values tested. The space complexity, however, would remain O(1), since only a few variables are used. In contrast, the optimized solution eliminates the need for nested loops by observing that the minimum cumulative sum determines the smallest required start value. This reduces the time complexity to O(n), while maintaining the space complexity at O(1). The big O analysis of the optimized solution confirms its efficiency. For time complexity, each element in nums is processed exactly once, and each operation within the loop, such as updating the cumulative sum and finding the minimum, is constant time. Therefore, the total work done is n iterations multiplied by O(1) work per iteration, resulting in O(n). For space complexity, the solution uses only two variables, current_sum and min_sum, regardless of the size of the input. This means the total memory usage is O(1). The optimized algorithm is significantly more efficient than the brute force approach, especially for large input sizes, as it reduces the time complexity from O(n*(m) to O(n), while keeping the space complexity constant. When tackling this problem, there are a few common mistakes to watch out for. One frequent error is misinterpreting the problem statement. Some might assume that the minimum start value is simply the lowest value in the array, but that's not the case. The key is to ensure the cumulative sum never drops below 1, which depends on the way numbers accumulate step by step, not just the smallest individual number. Another mistake is skipping edge cases. For example, in arrays containing only positive numbers, the result is always 1 because the cumulative sum is inherently positive. Similarly, for small or empty arrays, you must carefully consider the problem constraints to avoid unexpected errors. Finally, an incorrect iteration logic can also lead to issues. Dynamically adjusting the starting value during the iteration might seem intuitive but is incorrect. Instead, the goal is to pre-compute the minimum start value upfront to ensure the cumulative sum remains valid throughout the process. Another pitfall is overcomplicating the solution. Some might use nested loops or unnecessary data structures, such as recalculating sums repeatedly, but this is inefficient. The problem only requires a single pass through the array to compute the minimum prefix sum, which determines the result. Time complexity is another area to be mindful of. Approaches that recalculate the cumulative sum for every potential start value can quickly become inefficient, with a time complexity of n squared. For larger inputs, this is impractical. Instead, an optimized single-pass approach achieves n time complexity and is sufficient to solve the problem efficiently. Now, let's discuss some interview insights. This problem is essentially a variation of a prefix sum problem. The main insight is that the starting value needs to be adjusted to ensure that every prefix sum satisfies the given constraint. Recognizing this pattern can help you solve similar problems in the future. From an optimization perspective, the solution should be implemented in n time with 1 space. This is achieved by tracking only the cumulative sum and the minimum prefix sum encountered during a single traversal of the array. During interviews, it's also important to clearly explain why the minimum prefix sum determines the smallest start value. This demonstrates your understanding of the problem and your problem-solving approach. Additionally, you may encounter variations in interviews, such as constraints on the start value or arrays that require pre-processing before applying the prefix sum logic. Being prepared for these tweaks can give you an edge. Now, let's connect this problem to some related LeetCode problems. For instance, problem number 724, find pivot index, involves a similar prefix sum concept where the task is to find an index that splits the array into two parts with equal sums. Another example is problem number 238, product of array except self, which involves cumulative product logic but follows a similar prefix style approach. Then there's problem number 560, subarray sum equals k, where the focus shifts to finding subarrays that sum up to a specific value, again relying on prefix sums. Finally, problem number 53, maximum subarray, uses cumulative sums to efficiently identify the subarray with the largest sum. As for alternative approaches, one option is brute force. This involves iterating through potential start values and simulating the cumulative sum for each. While straightforward for small inputs, it's inefficient with n squared complexity. A more optimal approach involves computing the cumulative sum in a single pass while tracking the minimum prefix sum, which achieves n time in 1 space but requires a clear understanding of the prefix sum concept. Lastly, let's discuss another approach, binary search on the start value. In this method, you use binary search to find the smallest valid start value that ensures the cumulative sum remains above the threshold. This approach has a time complexity of n asterisk log max start value, which is less efficient than the single-pass solution but can be useful in constrained scenarios, such as when additional conditions are imposed on the start value. While it's not the most optimal for general cases, it's a good technique to have in your toolkit for more specialized variations of the problem. Great job on completing this problem. In summary, this challenge is a great exercise in analyzing constraints and using a cumulative sum approach. We explored an efficient solution with linear time complexity and constant space requirements. Remember, mastering problems like these strengthens your problem-solving skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!